It's a pleasure to present to John Krakauer. It's an honor for our scientific association to have the possibility to start our first day of Congress with John. I would like to start to say thank you to the volunteers and the scientific committee of this meeting. Everything is amazing, and today probably will be in the same way. And let's start to introduce to John Krakauer. Dr. Krakauer is currently John C. Malone Professor of Neurology, Neuroscience, and Physical Medicine and Rehabilitation, and Director of Brain Learning, Animation, and Movement Lab, the BLAM Lab org, at Johns Hopkins University School of Medicine. Dr. Krakauer is the co-founder of the company M Square Health and the creative engineering Hopkins-based project named CATA. CATA and M Square are both predicated on the idea that animal movement based on real physics is highly pressurable, and that this pressure is hugely heightened when the animal movement is under control of our own movements. A simulated dolphin and other cetaceans developed by CATA has led to a therapeutic game that has been interfaced with an exoskeletal robot in a multi-site rehabilitation trial for early stroke recovery and with motion tracking for cognitive therapy in normal age. Dr. Krakauer was profiled in the New Yorker in 2015, and his book, Broken Movement, the Neurobiology of Motor Recovery After Stroke, that I'm reading, and it's really awesome material, was published by the MIT Press in November 2017. We would like to thank you, John, in name of the Chilean Association of Movement Science and the Chilean Society of Adapted Physical Activity for your generous contribution with our scientific meeting and our disciplines. Whenever you want, John, you can start, and thank you again.
Thank you very much for inviting me. Can everyone hear me?
Yes.
Okay, all right. So I have quite a lot of material to cover, so we should get started. And I'll try and leave time for questions at the end. Okay, so what I'm going to be talking about today is just a little bit of a journey of some of the difficulties, puzzles, and perhaps even hope on how to think about recovery after stroke and in general. In other words, I hope that many of the principles here can be applied to other conditions. So this is just our website where you can, at BLAM Lab, where you can find many of the publications and other things. I hope it's pretty up to date. And this is the book, Broken Movement, that Pablo mentioned, which goes into some more detail of some of the concepts and the difficulties that I'll be talking about today. Let me just do this, okay. All right, so I think we'll start by just talking about what we all see as clinicians, which is the hemiparesis phenotype, and then we'll go on to talk about critical periods. So we've known about stroke for a long time. You know, the useful way of thinking about it, which caused a lot of puzzlement and investigation in the end of the 20th century and into the first half of the end of the 19th century and into the first half of the 20th century, was this division of, you know, stroke and cortical disease as being decomposable into sort of negative symptoms. In other words, loss of strength and loss of motor control, and then positive symptoms, you know, spasticity and synergies. And then the neurologist FMR Walcher, the dual nature of hemiplegia, you know, the combination of loss of voluntary movement and then this intrusion of positive phenomena, as I said, spasticity and synergies. So this is what we're facing, right? Stroke is really a mixture of a deficit and a movement disorder. All right, so we have a double problem to solve. Okay, and that's why it's been so difficult. So let's talk about the positive symptoms in a little bit more detail. These resting abnormalities and these synergies. I won't talk about spasticity today. So we've all seen this kind of patient with this postural abnormality, even when they're not trying to make voluntary movements, right? You depressed and protracted shoulder, the arm is adducted and internally rotated, you know, the elbow is flexed, the wrist is flexed, and sometimes even the hand is in a fist. Okay, so we've all seen this look in stroke patients. Now, looking at stroke patients over time, this is a very famous paper by Tom Twitchell in 1951, where he followed about 25 patients over time to watch the evolution of the hemiparesis phenotype. And he came up with this sequence. So you could imagine the patient is plegic. You could call that stage 0, which I don't have here. And then 1, you could imagine you begin to recover and there's some flexion at the shoulder. Then the elbow flexes. So you get this simultaneous co-activation of the shoulder and elbow. This is exactly what a synergy is, right? It's an unwanted co-activation of muscles or cross joints. That's called a synergy. And then you get the wrist and the fingers flexing. And then if you're lucky, you can sort of get out of that flexor synergy and begin to express an extensor synergy. So in other words, you begin to do extension at the shoulder and elbow. And then if you're really lucky as a patient, you can begin to do out of synergy movements. All right, so you can extend and flex out of synergy. So for example, you can extend the elbow and flex the shoulder. All right. And then if you're lucky, you can also get individuation at the fingers. And this sequence is variable, right? There's a lot of noise in this, but the basic idea is that you can go from plegia to synergistic movements to out of synergy movements. All right. So I'll show you this. So those are the two things that one should keep in one's mind: that postural abnormality that is present even when the patient is not trying to move, and then the synergy abnormality, which is a voluntary movement abnormality where you get unwanted co-activation across joints, you get synergies. Okay, so an intrusive postural disorder and an intrusive movement disorder. Okay. Now we'll go to the negative symptoms that Hewling-Jackson was talking about. And one of them is loss of motor control. So one of the ways you can study motor control in the lab, and maybe many of you have seen this, is you can look at planar reaching movements. In other words, you have someone seated at a table. The arm is raised so that the shoulder and elbow are at the same level. Then you can limit movements of the trunk with a high chair back. You can have friction removed largely with an air sled. And obviously the table is supporting the arm so that you don't have as a big as contribution of weakness. So it allows you to see what their motor control looks like in the absence of friction, in the absence of gravity, and in the absence of compensatory movements. Right. So in other words, what I'm saying is that the only way to get to the target, making straight movements like you see on the right, is you have to do motor control correctly. All right, there's no way to find a compensatory movement to make those straight movements you see on the right. So it's a nice test of arm motor control. It's very important to understand that this is an assay. It's not a task. It is really an assay of the capacity to do motor control of the arm. You should consider this the arm version of testing individuation of the fingers. Okay. And, if you look at a patient with a moderate stroke, as you can see on the right, you can't make those straight movements, right? The paths are not smooth and straight. There's high variability at the endpoint. And the big question is can you get from the movements on the right to the movements on the left? And you can quantify those movements. We found a way of taking that visual impression of that obvious difference between the right and the left and coming up with a way to mathematicalize that. So that's what we did here. So all you need to know is that we have a kind of mathematical measure of the abnormality of the curvature of the movements on the right as a function of how different they are from normal movements. And then on the bottom, you can see that you can track that number over time. And basically, you can see that you improve the quality of those movements over the first 4 weeks, and then you stop improving. Okay, and if you look at that dotted line at the bottom, that's what healthy controls look like. Okay, so there's this big white space that you don't improve over. All right, so there seems to be a window over which you can improve your motor control, maybe a little bit up to 3 months, but then it flattens off. All right, now it's a little bit, when you decompose this, it looks as though if you're mild, you can do most of your recovery early, and if you're severe, you can continue to improve maybe over 3 months, but really even overall motor control begins to plateau after 3 months. So we don't have much time therapeutically. Now, what's interesting is that I've just told you that I'm considering stroke a movement disorder with the postural abnormalities and the synergies, and a motor control disorder. And now you can see that you can dissociate these, okay? That these components in a patient are not all equally severe or highly correlated with each other. So let's go through this. So one way you can look at the postural abnormality that I showed you with the patient is to take somebody on a surface like I described and passively move their arm over the surface without asking them to do it. So the robot just moves their arm into different positions on the surface. Okay, I hope that's clear. And then what you can do is you can measure the forces on the handle of the robot that are being exerted, even though the patient is being asked to fully relax. Okay, so the patient's told, just relax, hold onto the handle, and the arm will pull you all over the place and record the forces at each of those locations. And what you can see is that they can't relax, right? They generate forces, flexor forces, that are basically directed towards their body. Okay, so this is basically just showing color isotherms of the force field. And here the red dots are just particular locations we looked at. And you can see that there are forces being exerted even when the patient in their left paretic arm is trying to relax, whereas it's much easier for them on their right unaffected side to just relax. Right? And what you notice very interestingly is that if you give them more weight support, so we did this with a robot, you can get rid of these postural forces a little bit. So in other words, this synergy at rest, this postural abnormality, sorry, I shouldn't call it a synergy, this postural abnormality can be mitigated by weight support around the shoulder. All right. Others have shown this for synergies. This is an example for the resting abnormality. All right. So you can, just to make it clear, you can use more detailed behavioral characterization to take a look at some of these components of hemiparesis. So this is an analysis of the postural abnormality. And then what you can do is you can relate that postural abnormality on the y-axis with your ability to make actual movements. Okay, so in other words, you could imagine maybe that if you have regions of the force of the workspace where there's a force, even when you come to rest, maybe it will be difficult to move to those locations, right? So is there an interaction between moving and trying to come to a stop at those locations where you cannot relax? All right. And fascinatingly, we find no relation. Okay, so in other words, the abnormalities at rest and difficulties during movement are not correlated. Now that's important, right? Because it means that all these different components of hemiparesis are going to have to be targeted independently by treatments. This is just to give you the reaching version of this experiment, a sort of very well-known set of experiments by Jules DeWald, where they basically look at the area that you can reach by extending the elbow. And as you can see, you can barely move, and then you get better and better as you provide more weight support. So this is the movement equivalent of the weight support that I showed you for the resting abnormalities. Okay, so the area that you can cover on the table surface, mainly by being able to extend the elbow, is improved by increasing weight support. Now understand how unexpected that is. The weight support at the shoulder cannot have an influence assistively on extension at the elbow, and yet the area that you cover increases. So somehow weight support at the shoulder, both with postural abnormalities at rest and with the synergies during movement, which prevent the elbow from extending, can be mitigated by weight support. Okay, and I don't really have time to go into the full argument as to why that might be. Now, what I'm showing you here is very preliminary data from from a monkey model that we've just started to develop for studying synergies. So one of the problems with the animal literature of stroke is that the positive symptoms, which cause such trouble for patients, have not been reproduced in animal models. So the animal models have weakness and they have loss of motor control, but they don't have synergies. Okay, and in fact, if it's of historical interest to you, when they've started in the 20th century to make pyramidal lesions in monkeys to make a model of stroke, the pyramidal lesions caused hemiparesis, weakness, and loss of control, but they didn't see synergies. So the word extrapyramidal, which is often used today as a movement disorder term, came because they said, well, the synergies must be coming from some extrapyramidal location. Okay, and we have had that problem up to the present day. Where is this extrapyramidal location? Right? So with Stuart Baker, we've begun to start doing some experiments to try and impose lesions in various cortical regions to try and reproduce synergies in a monkey model. Now, I'm not going to go into great detail here. This is preliminary, but suffice to say that there is some evidence with lesions, in the anterior motor cortex at the lip of the junction between the motor cortex and the premotor cortex, that you can in fact begin to see some evidence in a monkey model of turning on of unwanted EMG in the flexors. Okay, so this is very preliminary, but I hope you understand that if we're going to treat the positive symptoms of stroke, we're going to have an animal model of it. And some people are surprised when I tell them that to this day, we do not have one. And this is why we're trying to develop in this monkey model. Now, to continue with this uncoupling, I've just shown you that the postural abnormalities and the synergies don't correlate. Now we're going to have a look at what the relationship is between synergies and motor control. So here's nice motor control in that task that I showed you before. Here are some chronic patients trying to do this task, and these are their Fugl-Meyer scores. As you remember, the Fugl-Meyer score was developed to provide a number to quantify the Twitchell sequence that I showed you at the very beginning. That was what the Fugl-Meyer score was for. It was developed to quantify synergies of the Twitchell kind. Unfortunately, what's happened is the Fugl-Meyer has become a general measure of impairment. It was never intended to be that. It was intended to be a quantification of the Twitchell sequence of going from synergies to out of synergy movements. And the point I'm making can be seen here, because if you take acute patients, right? So these are patients within the first 3 months, these are patients after 6 months, and you put them in the same Fugl-Meyer range. So for example, this patient has a Fugl-Meyer of 29, the lower it is, the worst. This patient actually has a better Fugl-Meyer of 33, but look, their motor control in blue is worse than the patient with a worse Fugl-Meyer. And you can see this all here. Here's a 42, 29, this is worse in blue, and you can see this all the way across, okay? And you can actually quantify that. Here's the Fugl-Meyer score, acute and chronic. You match them, right, for the Fugl-Meyer. And yet when you look at their motor control, the quality of their trajectories, the acutes are much worse than the chronics, right? So matched for Fugl-Meyer, not the same for motor control. So here is another dissociation between the negative symptoms, the motor control abnormality, and the positive symptoms, the synergies. All right, so I hope you're beginning to see the picture that hemiparesis is made up of components that are not related to each other, other than that they're all caused by the stroke, of course. Right. So I hope you can begin to understand that when you come up with a treatment for patients, you need to identify which components specifically you're targeting. It's like Parkinson's disease, right? Tremor, rigidity, and bradykinesia are different. Hold on one second. Have a wonderful trip. So basically then, I've shown you a sort of decomposition of the hemiparetic deficit into motor control, strength, synergy, and then compensation, which I've tried to avoid because we don't let them in that setup. And then you have a mouse, a monkey, and a human. And then here we have a ruler, which means, can we measure these abnormalities? And then this is, can we fix them, all right? So in the mouse, we know there's a motor control abnormality. We know there's a strength abnormality. They don't have synergies, right? And we've actually shown in mouse models and so have others that you can in fact fix these things. In the monkey, again, you can have motor control and strength abnormalities. You can fix them. Synergies, we don't have a model for synergies in either the monkey or the mouse. And then the big question in humans is, can we do anything for the motor control abnormality? And can we do anything for the synergies? All right. So I hope you can see the landscape and the big problems facing us, right? We have both the negative symptom problem and the movement disorder problem. And we don't get help from our science over here, other than the monkey model that we're working on now to address this. All right. So now I'm going to switch and show you something else, which is this interesting notion of critical periods and the fact that we might not have an equal opportunity to affect these components if we go chronically compared to if we go acutely. All right. So I'm going to show you work by Steve Seiler. He had an NIH grant with me. He's now an associate professor at Hopkins and continues to work with me. And I'm going to show you just some of the work that we did in the mouse. And then, you know, if you're going to do mouse models, you're going to have to make some sort of evolutionary argument that what you work about, what you find out about in the mouse is justified to apply to humans. And very interesting work has been done looking at homologies, both in physiology and in behavior, to make the suggestion that you can learn something that is generalizable to humans from the mouse. And this is just Kolb and Weishaw making the claim that, you know, the way that a reaching movement is made by a rat, for example, and a human has the same stages, like the start, the lift, the advance. I won't go into it in more detail here, but I do think it's important when you look at mouse experiments to feel like there is a reason to generalize the results. Here's a mouse reaching. I think it's quite a surprise for people who don't work with mice or rats that they do actually have quite dexterous movements like that. This is when the mouse has not learned to pick it up, so it's quite hard for them, but you can train them so that they can pick that pellet up in one movement and get it into their mouth. Okay, so you can train them, and then you can give them a stroke after the training. This is a coronal section through the mouse brain, and this is its motor cortex. And you can basically put a stroke in that motor cortex, and then you can have a look at the effect that stroke has on the movement. So this is training the mouse over about 10 days. They get to about 60%, 55% efficacy. Then you give them a stroke that I showed you. Obviously, they get much worse. You wait about a week. Okay, so this is like a human, right? You don't have the training phase, but you have the stroke, then you're on the acute stroke unit, and then rehab starts, all right? And even though you train the mouse on the same task every day for 3 weeks, you can never get them back to the way they were before, all right? So that looks a lot like what happens to humans. What can we do? Well, we can go early. So you do the same thing, but you don't wait. You start training them within a day. Back to normal. Okay. So that's very surprising, but it's also interesting that there's a window in the mouse where the same amount of training is much more effective if you go right away than if you wait. So now I'm going to show you something really weird, which is we're going to do this experiment again. You train the mouse, you do the stroke, you wait 7 days. Again, you do all this training, you can never get back to the top. And now we're going to give them another stroke. Okay, so we're going to do something very strange, which we're never going to do, obviously, in humans, which is you give the mouse a second stroke near its first stroke. And you're going to see that the mouse gets worse, obviously, because now you've increased the infarct size. But now we're not going to wait the 7 days, right? We're not going to wait the 7 days. We're going to start training right away after this second stroke, back to normal. So this is a very spooky, interesting result. You basically treated the first stroke with a second stroke, made them worse, but because you started training immediately rather than waiting this week, you actually treated this stroke. All right. So in other words, there's something about stroke and the early critical period that is telling us we need to start training right away. And if you remember Alex Dromerick, who regrettably passed away, but his study CPAS was published in PNAS several weeks ago, showed that this is also true in humans. You get more effectiveness of training early than going late. And it's not a non-specific effect, because if you put this second stroke, for example, in the occipital cortex, you get no benefit. So in other words, you have to put the second stroke in a region of the brain that is motor so that it has access to the spinal cord. And I won't go into great detail on this slide, but a very similar result was obtained in 2008 in the monkey. Okay, so they had monkeys trained to do this task, which is to take pellets out of small wells. And the point is that the only way to be able to take the pellet out of the smallest well is to do a proper precision grip, opposing the forefinger and the thumb. And basically, if you trained aggressively early on this task, this is the monkey that got trained on that task. After a month, the pink indicates how close they got to being the way they were before. Whereas if you don't train, the pink is here, the pink disappears, and this is all compensatory movements. Okay, so in other words, you have to go early and intensely to try and reverse the deficit. Otherwise, you just end up with compensatory movements. So in the book, I basically write out this heuristic equation to explain all these results in the mouse, the monkey, and the human, which is that if you want to actually reverse the deficit, restitution, then you need to have a high dose of behavior. you have to have some residual neural architecture that has the capacity to control muscles via the spinal cord, and you need plasticity. So as I showed you, plasticity is higher early than late. So if you have a high degree of plasticity early, the same amount of behavior can lead to an increased amount of restitution. And then you're more likely to have good use of the plasticity and the behavior if you have some residual architecture to operate on. Reorganization that everyone talks about, where one area takes over another, doesn't exist, right? I could give another talk about how people have very much misunderstood the idea of reorganization. You don't get reorganization. What you get is upregulation of pre-existing representations. Okay, so what do we do about all this, right? I've talked about the components, I've talked about critical periods. So what are we going to do? Well, we're going to have to find a way to repeat those experiments that I showed you in the rodent and the monkey and try and do it in the human. So how are we going to do that? Well, we know that three things are very helpful for neurological injury. One is enrichment. In other words, 75 years of evidence to show that animals that are put in cages with toys, with friends, with spaces to explore, show more changes in their brains than if they are just in a cage alone. We know that physical exercise is important for brain repair. And then we know that obviously training on the capacities is important, right? So basically what we need, ideally, is A plus B plus C. All right. So how are we going to do that? Well, this is just to show you a nice review that appeared in Nature Reviews Neuroscience in 2019, basically showing you why and all the different levels of effect these enriched environments have, okay? So it's a very interesting science. It's multi-scale, multi-level, it's complex, but we know that it's all these ingredients together that are important. And unfortunately, we have a tendency in medicine to always want to look for the critical ingredient, to find the one thing that is working. And what I'm going to say to you is there is no one thing, okay? You're going to have to do all of the things, okay? You had Daniel Wolpert speaking, I heard, and this is a study that he and his team did, back in 2009, where they basically looked at what the movements are that we all make with the upper limbs in the course of a day or two of everyday life. And interestingly, all of us live, for the most part, in this statistical cloud of movements, okay? Whether you're gesturing, whether you're eating with a knife and fork, driving, we use our arms in these very interesting spaces, okay? So, okay, that means that maybe we need to create an enriched environment for humans, and we need to promote playful exploration in those statistical clouds outside the context of a specific task. Okay, so that's why I'm showing you this, right? I want to make a case that we need to do exploratory movements that are not fixed on any given task, and they happen in an enriched, playful situation. And a clue for us came from Disney. Animation actually means movement, right? So in other words, we like to see characters moving in beautiful environments, all right? So we have to go one step further and basically be the character in the environment. So in other words, the way that you combine the enrichment and the training is to be the character in the animated environment. So we did a small trial to test all these ideas. That's me just demonstrating the situation. So basically, the robot here was used not for assist, it was purely for weight supports. In other words, this is the equivalent to the table, but it's for three-dimensional movements, right? The table is good weight support for two-dimensional movements, but the robot here was supporting three-dimensional movements. Okay, so it allowed you to do motor control in the presence of weakness. And then the goal is to become a dolphin character in the ocean, and you explore, as you steer the dolphin in the ocean, all the kind of movements that you could see in that statistical cloud from the Daniel Wolpert study. Okay, so I hope you can see the logic here. And so this is a very small study. It's very difficult to give patients this much training. In other words, they had to do an hour time on task in the morning, an hour time on task in the afternoon, 5 days a week for 3 weeks, in addition to their regular therapy, and they had to be within the first 6 weeks of stroke. Okay, so it's a lot. It would be like having a tennis lesson twice a day, every day for 3 weeks. Okay, so that was the goal. And then we did have a control group that was not regular care. It was the therapist also doing an hour in the morning, an hour in the afternoon, 5 days a week for 3 weeks on top of regular therapy. Okay, so these were two different ways to give a lot more therapy. Okay. And I'm going to show you what it looks like. Tell me if you can hear this. So this is basically what the patients see, right? So you're steering the dolphin and you have to eat fish. So you're in a room with a big screen. You don't see your arm. You just see Bandit the dolphin. And the patient doesn't realize that they're making these big amplitude movements to try and play the game. And it gets more difficult as you go through the levels. And at one point, you start to battle sharks. Okay, I think you get the point. And what did we see? Well, this is really interesting, right? So this is a slightly confusing slide. This is published, by the way. This is the ARAT score. Okay, so this is a prehension task, specifically looking at essentially negative symptoms. Can you make a reaching movement and a prehension movement? And here's the Fugelmeyer, which we talked about today, which is looking at positive symptoms, right? And this is the baseline, and this is after those 3 weeks. And what you see here in blue is we were lucky enough, Gert Kwakkel, who's a well-known rehabilitation expert in Holland, has a very big database of regular rehabilitation over time in the same time window as our study. Okay, so we were able to compare our two intense groups with regular care in a large number of patients. And each blue line here is sampling the same N as we had in our study over and over again. So it was like we had lots and lots and lots of groups of 21 patients that we could look at to compare to what we did. And what's interesting is that on average here, what we found is that our two intense interventions, we found that both high intensity extra regular care and the dolphin both were twice as effective as regular care. Okay, so this is sort of the average here, and this is what we got here. All right. So that's basically nice because it basically confirms what the monkey and mouse studies showed, that if you do more early, you do better. Okay, but at least in this small study, even though there was a trend, the positive symptoms did not benefit from extra, either dolphin or extra therapy. Remember, this is early after stroke, so spontaneous recovery is happening, and we're looking for effects that are better than spontaneous recovery. And we were able to do considerably better than spontaneous recovery and regular therapy for negative symptoms, but we weren't able to do better than spontaneous recovery or regular care for positive symptoms. Okay, so this is really important. It shows all those data that I showed you about the dissociations early. It's showing that the different components of hemiparesis do not respond in the same way to an intervention. All right. Now, this is a small study. This might be underpowered. We're doing a much larger study with Kathy Stenier and Winston Biblow that's ongoing right now with 150 patients with the dolphin. And we'll see whether this dissociation remains true. So why is restoration of motor control in the upper limb so hard? Well, there's a critical period that closes. Stroke is a nasty thing in humans because it's a deficit disorder and a movement disorder. Chronically, we don't know if training alone will be enough, although there are some studies suggesting that you still can benefit from highly intense interventions chronically. But we might need to be doing new things in patients and chronically, including perhaps, stimulation and drugs with a backdrop of high intervention, high dose behavioral treatments. So I hope you can see that this is a complex disorder, and simply treating a patient as a single deficit that you can do regular therapy on is never going to help us. A lot of people involved in all these studies, Andy Luft, Mogo Krakauer, Pablo Selnick here at Hopkins, Johan Dietrichson, lots and lots of different funding and lots of other people involved. This is team science. If you want to get this kind of work done, a single investigator with a single grant, it doesn't work. And then even more importantly, you need a different team. So this is the team that made the dolphin, right? You need computer scientists, software scientists. This is an artist. He's done work for Marvel and for Disney. Omar Ahmad worked at Disney before he joined us. Prameet worked at Microsoft. So you need, in addition to the clinicians and the scientists, you need these remarkable young engineers and artists who work in parallel to the clinicians. And unfortunately, this idea that you need these kind of people in the hospital working side by side with the clinicians is a new idea, but we're not going to make progress in human neuroscience unless we invite these kind of remarkable people into the mix. Okay, I will stop there if that's okay and take questions if there's time.
Yeah, thank you, Jan, for your amazing talk. Let me start with a question for the audience. The first question is how we can differentiate the spontaneous recovery and the motor learning in early rehabilitation in humans. If you suggest something to differentiate motor learning to the spontaneous
recovery. I mean, I think I just showed you, right? You have to have measures where you compare a group that just gets regular care. And in my view, regular care just doesn't do anything. So you just see spontaneous recovery. And motor learning is not what's relevant to recovery after stroke. It's training. Okay, training and motor learning are not the same thing. When you train in the gym and you change the size of your muscles, you don't say that your muscles have learned anything. Okay, so I think it's very important, like we tried to show with the dolphin, we tried to do better than spontaneous recovery, right? And we did. Okay, so training of motor control compared to a control group does better than spontaneous recovery, right? So if I understand the question, you just have to have a control group and you have to be able to measure the effect of your intervention. And, okay, and the intervention is a form of training. So to the degree that the questioner thought that motor learning and training are kind of the same, then, I think it's very clear. You have to do a trial with a control group.
Yeah, however, in the Krakauer results showing the full Mayer trendings over after the stroke, we can see different progressions in the full Mayer and a different proportional recoveries rate. And I don't know if it's important to select very well the patients.
Pablo, can you repeat your question, please?
Okay, yes. Can you hear me now or not?
I can, but I was translating and I couldn't hear.
Okay. However, we can see different progressions in the Fugl-Meyer recovery.
But when you say different progression, you mean the Fugl-Meyer didn't improve the way the ARAT did. Is that what you mean?
Yeah, some patients show.
I mean, are we talking about the result that I showed, or you're making a point outside of the study that I described?
Yeah, no, outside. The Krakauer, the Holland researcher that
yes, yeah,
yeah, show different curves in this study. Some people
that
you
mean you're talking about one of the studies? Yes. In other words, there he was trying to do a sort of mixture model of proportional recovery.
Yeah.
So that whole study was looking at different subsets of patients with Fugl-Meyer's, but that's fine. But that doesn't. But if you have a matched study, right, and you have the same distribution of severities, which we did, then all we're trying to see is in any patient, can we do better than spontaneous recovery, right?
Agree. I understand.
And the answer is right now, no. I mean, Krakauer did a study with constraint-induced movement therapy early, and we've now done this one, and we were not able to do better than spontaneous recovery on the Fugl-Meyer. The CPAS study that was recently published by Dromerick and colleagues, the outcome measure they used was the ARAT. And there they showed as well that you do better if you go early. So everyone is showing ARAT improvements, but no one at the moment can show Fugl-Meyer improvements early.
Thank you. And the next question is, from your point of view, where should the following research on the rehabilitation stroke patient be oriented? What is the next step?
Well, I think we need to do much larger studies focusing on movement quality, negative and positive symptoms early after stroke. In other words, we have to do much bigger and more aggressive studies early. And we need to move away from task-oriented training and compensation and focus specifically on the capacities, whether it's the motor control, the weakness, or the synergies. Okay, so we have to learn to do, much more aggressive, high dose, high intensity interventions early.
Great.
I mean, almost all studies have been done in chronic stroke. And most importantly, we have to stop worrying about function, and we have to start looking at impairment.
Great. Thank you. The next question is, great presentation, Professor Krakauer. I would like to ask you the following. At different times, you mentioned that the recovery of motor control follows a different path than the recovery of weakness. I would like to know what are the aspects of motor control that you identify as critical, considering that we have always studies of force control as a component of motor control.
Always studied which of the component of motor control?
Sorry. The force control or strength?
Yes, I mean, yeah, I understand the question. So there's a big difference between the generation of high forces and the generation of sub-Newton forces. Obviously, even for finger individuation or motor control, you have to generate some force. But the important point here is that when you do grip strength, when you generate high forces, that is a different neural system than when you generate small forces for dexterity. So in other words, the corticospinal tract is much more important for the small forces required for motor control, whereas other tracts like the reticulospinal tract are necessary for high forces. So don't confuse high forces, strength, with low forces for dexterity. The word force is used in both because it is force, but they're different.
Great. The next question is, in relation with the ABERT study.
Which study?
Albert, that the Australian researchers performing the early rehabilitation.
Oh, avert.
Yeah. About. Sorry.
Yeah.
Spanish. What is your opinion about that? The results show a negative result before the 24-hour.
So the avert study, unfortunately, is completely misunderstood by everybody. Okay, the avert study was really two types of result that people don't read the paper carefully, right? One was a very, very tiny difference between going, and let's be clear, what the avert study was a study of getting people up out of bed, right? It was, training on standing and locomotion, and whether one should go within the first 24 hours after a stroke or afterwards. But more importantly, what it was a study of in both groups was going early within the first 24 hours and doing 3 times more training of standing and balance. Okay.
Right.
And what they found was that the group that did the 3 times more training of standing and balance did a little tiny bit worse than the group that didn't get the extra early rehabilitation. But the problem with that study is that they didn't control for the fact that if you have a large stroke and you stand up, because of problematic autoregulation, you increase infarct size. So this study was completely confounded by the fact that all of the worsening, the small amount of worsening, was in patients with large cortical strokes and hemorrhages. So the result can be completely explained from having people with impaired autoregulation early, standing them up. It had nothing to do with early rehabilitation at all, that study. That study told you that you shouldn't stand up early after stroke. It didn't tell you about rehabilitation early after stroke. What should have been done in that study is having them remain in bed and have them do an arm task early after stroke. And then you wouldn't have seen a problem, in my view. You've seen the opposite result. So unfortunately, the AVERT study tells us nothing about early rehabilitation. It tells us don't stand people up early for long periods of time with large cortical infarcts or hemorrhages. Do you see?
Mm-hmm.
Very important. But because people who read the AVERT study don't know much about the neurology of stroke early, they misinterpret the results. It's very, very important to understand that. And I go into detail about this in the book. But I can't tell you how tired I am of hearing about the AVERT study as though it told us about whether you can do early rehabilitation or not.
Mm-hmm. Great. The next question is, excellent presentation, John. And how much training is enough? Is there any systematic study of dose response to guide rehabilitation prescription to go above proportional recovery?
Well, I mean, we don't know exactly, right? In other words, but we do know from the animal literature that you have to do thousands of repetitions, right? And we do know from studies now in other areas like treadmill training, spinal stimulation for spinal cord injury. We know in chronic stroke for an effect on something like the Fugl-Meyer that you need to do 5 to 6 hours a day, right? So in other words, we don't know exactly what it's going to have to be, but it's going to, in my view, you're going to have to do at least an hour to 90 minutes time on task. Just make me very clear. 60 to 90 minutes of movement. You can't count saying hello, them taking a break, setting up the apparatus, right? And the average time at the moment spent on task, as you know, time on task in an acute upper limb rehab session is 11 minutes. Okay, and when you look at an hour of therapy and you actually measure time on task, it's terrifying how little time is actually spent moving. So in other words, you need to go from 11 minutes to 90 minutes at least. All right. In the study that I showed, it was an hour in the morning and an hour in the afternoon, which meant that the therapist had to spend 5 hours in total with the patient. Okay, so I think you can see that the doses and intensities of current therapy are essentially useless.
Great. Probably the last question for the time. The question is about objective way to measure the compensation during the rehabilitation. What do you recommend to measure?
Yeah, that's a very good question. In other words, there are two ways to deal with the problem of compensation, right? One is to measure it directly with motion tracking, and then hope that you can use algorithms to separate the compensatory part of moving from the true reversal of injury. Or you can do what we did, is you do assays like the two-dimensional table and finger individuation, where you remove the possibility of compensation from the assay. So in other words, you have to make a decision whether to separate training and assessment, and train and then assess with assessments that remove compensation. Or I think where the future is going is we'll be able to actually look at the full three-dimensional movement and separate out compensation from reversal in the actual three-dimensional movement. But so far, very few people are doing that.
Okay, maybe I can ask the last thing. Mauro asked you if there are some intervention to manage the synergy problems in patients after stroke, about the positive signs.
Yeah, that's a great question. In other words, one approach is to try and use weight support that gets titrated, like Jules DeWolde. So in other words, you take the weight away and then slowly take away the weight support and hope that that's a way to train away synergies. There are some people like Mark Slutsky in Chicago doing operant conditioning paradigms. Some people are using functional electrical stimulation. There's a study going on in Europe that way. So it's a challenge, right? We are going to have to find a way through those different techniques to get at the positive symptoms. So it's an open question. I'm hoping that in the study we're doing in New Zealand with weight support that's titrated and going earlier, even earlier than we did in our study, that you might prevent the onset of synergies. But it is the $1 million question, right? And I think now at least you understand why it's such a problem.
I'm so sorry, but I had to cough and I silenced myself and I couldn't come back from the last two questions.
Okay.
So now I'm just on track and I couldn't tell you. I was texting the guys.
Okay. Oh, okay. No problem. Don't worry. Okay, John, probably I can continue asking you a lot of questions. Very interesting talk. I would like to say thank you in the name of the organization. And I hope that we can stay in touch in future to learning more about your amazing research. Thank you, John.
And thank you for inviting me. Take care. Bye-bye.
You too. Bye-bye.